Good morning. So my name is Paul Murray, and I've been working at Stanford University for about 30 years now. So yeah, if you do the math, that means I probably started when I was 10 years old. I first started out as a network consultant, basically advising the departments how to configure the local area networks. I moved into becoming the manager of that group for a number of years. Then I left and went to industry, and I worked for a wireless signal processing group. We helped develop 3G, which back then was very evil as well. I came back to Stanford as the manager of the same consulting group, but I decided I wanted to do a more technical role. So I went ahead and became a backbone engineer for a number of years. But for the last 8 years, I've been one of the 2 network architects. So today we're going to present volumetric DDoS. And what I'm going to try to do is present it in slightly layman terms so that you don't have to be a network engineer or a security professional to understand this. And I'm going to start by presenting a history of Stanford's DDoS, how we arrived at needing a DDoS solution. We're going to talk about what exactly the Corero solution is, how it works in the Stanford infrastructure. We want to look at the Stanford topology specifically. Then we're going to discuss how we tuned the product over a year, because with any of these kinds of tools, you have to baseline your traffic and make sure that the tool actually works correctly with what your traffic looks like. Then we'll look at some specific examples we have. Okay, so it was back in 2009 that I first became aware of DDoS attacks on the Stanford campus. This was back in the days when we had 4 connections to CNIC, and each of them was 1 gig. The network kept melting from these DDoS attacks, and we quickly figured out it was large amounts of UDP traffic. But the problem we had was we didn't have adequate detection. So we would always jump from router to router, trying to figure this out, look in our flow tools, that kind of thing, try to determine where we needed to put the filter. We were essentially playing whack-a-mole. So the thing to take away is we had poor detection of attacks. So this was back in the days when we had these really cute names for what we called operational zones. We had a Bozy, a Rosie, a Cozy, a Dozy. It almost sounded like a Snow White and the 7 Dwarfs. Well, this is actually something called TOSY, which is the test operational zone. So what we did during the DDoS attacks back in the day was we took 2 of the spares for our network. We threw them into a lab along with a brand new Cisco ASR. And we wanted to get a Juniper MX, but they only offered us an M7 at the time. And what we did was we passed packets from a Spirent bit tester through the network, and we tested each of these devices. And what we found was no matter what we did, the Cisco 7301 would just roll over. But we found with the Cisco 7201 that if we removed the border access list, it was a very fine router. But the problem was we couldn't remove that filter because it's the kind of thing that protects us from Microsoft window port scanning, SNMP traffic, that kind of thing. The other thing we found out was the Cisco ASR and the Juniper M7, they could not be taken out. But it was around this time the Juniper sales team went out. They did a very interesting thing. They went and got somebody from Sunnyvale to come in, and they basically showed us how to fire off a policer from a script so that when the specific attack traffic came through, we could essentially squash it. Now, we didn't use this to stop DDoS back in the day, but this became very valuable for us to protect attacks against some of the infrastructure on campus. Specifically, our www was a frequent target of attacks, as was, we all heard of the NTP reflection attacks. So we had this policer in place from day one on the Juniper routers. So this essentially led to us having the first Juniper router on our campus. We upgraded our connection pipes to 10 gig. And then we got our second MX and our third MX, and everything upgraded to 10 gig. So we sat there and we were kind of running a victory lap at this time, because what we found out was we were no longer having the network layer melt. Border routers were no longer the issue. And as far as we were concerned, we'd beaten DDoS. The bigger network pipes, it seemed, or the upgraded hardware were very hard to target. But it was around this time we started to get alerts from other devices in our network. So I think the failure points were starting to change. Our load balancer sysadmins would come saying, wow, I've got this syslog that says a DDoS attack happened or something else that was alerting. then the firewalls would fail in mysterious ways, and we would see maybe session exhaustion attacks or some other type of incident that looks suspicious to us. And then finally, we would get attacks to our www infrastructure, which back in this time of 2010, 11, 12, was still on the Stanford campus. We hadn't yet moved it to the cloud. So we started to ask ourselves the questions, were these other points of failure due to DDoS attacks? Now, remember, I keep going back to this. Our detection was minimal, and it was only ever done in a post-mortem fashion. We were the networking team, after all. We operated the network. We were looking for congestion, errors, flapping. We were in a constant cycle of doing backbone upgrades and maintaining the network. We were busy, and we weren't really the security office. I came up with the motto back then when the security office would put out all these security mandates. Everyone would think it was the networking team. And I used to say in these public meetings, hey, we're networking. We pass the packets. So we really only went looking for information from our flow tools when something significant happened. And when we did find evidence that there had indeed been DDoS attacks. So we basically spent the next decade without an actual service. And we kept asking ourselves, do we actually need DDoS? So it's around this time over this decade that we need to call out to CNIC, because the excellent efforts of CNIC led to the level 3 DDoS service that they provided. And the CNIC community that we're all a part of here, the TACs were discussing the Internet to DDoS solution. And CNIC had also reached out about some other security measures during this time. There was something called MANAs, which is the mutually agreed norms for routing security. So this was all put on the radar by CNIC and the CNIC community and kept in the back of our mind. But it was about a decade later, after we'd upgraded these first routers, that the pandemic hit, and we had a little bit of breathing room. So we sat there and we kind of looked at some data. We looked around, we looked at the information from the sysadmins, and we still didn't know whether we needed DDoS. So we went and asked the experts. So we talked to the security office, and there was really no push for a DDoS solution from them at that time. And the reason for this was because they were focused on the stealthy infiltration things that were happening. They were essentially trying to protect the assets of the university. And we asked them basically, like, hey, there's this solution from Internet 2, the Radware solution, do we need it? And they said, well, this is kind of low on our priority list right now. So they were really focused on protecting the PII assets of the university and preventing lawsuits and the leaking of PII. What's interesting is, so pre-COVID, they had this stance, but then this happened. And this is kind of interesting to put up on a slide because it's, a current event. Well, I got this Slack message one day in February of 2023 from one of the security guys, and he was sort of in a panic saying, we kind of need DDoS. And what I found out was there was a Russian-aligned group called the KillNet Activist DDoS Group. And he was very concerned because they were targeting infrastructure, I think, throughout the US and the world. And he was basically kind of saying like, oh, we need DDoS. So I just texted him back and said, hey, don't worry, we already have it in place. So the timeline of this was essentially that in September of 2020, when we had this little bit of downtime, I kind of heard a Corero sales team from Juniper said, hey, we have this new thing, why don't you go look at it? But it took us until April of 2021 until I actually went to a demo. I was like, wow factor. I was like, this seems to be checking all the boxes we need. So I quickly set up a demonstration for our entire backbone team. They liked it as well. And 6 months later, February of 2022, we basically acquired funding. Now, if anybody of you work in academia, you'll know 6 months is like, it's instant, right? So we got to thank our senior management for getting the funding for this to support this right away. Things do not happen that fast in academia. We took possession of Corero in May of 2022, and within 1 month, we had it up and running in an operational fashion on the network. But it took us about a year before we were able to put it into fully automated mode. So what else had we looked at in that time? So over that decade, we'd looked at the solutions in the cloud, like Cloudflare and Akamai and Azure and AWS. But what we'd found out was we had these two groups on campus called computer science and electrical engineering. And I don't know what these kids did, but they always upset somebody somewhere around the world. So there was no protection for university assets in this model. And I think I've already spoken about this, where Scenic was really ahead of the game. So they had this level 3 solution, but it was really aimed at institutions with smaller pipes, and it didn't have an IPv6 solution. And then the last thing that I was a part of at the time was this discussion around I2 Radware. I think this is an absolutely fantastic solution. It kind of works like a family phone plan. So let's say you get 10 universities to sign up under Scenic. Each one maybe signs up for 2 or 4 gigabits per second. And during an attack, you're able to bundle that so that the actual targeted site gets maybe 20 or 40 gigabits per second of protection. It's really, really a great solution. But the problem was, at that time, it didn't have detection. Now, that's actually changed because there's actually a talk, I think, tomorrow about the DDoS detection solution that Scenic uses. So this is actually old information, but at the time, this is kind of what was going through our mind. And then the final thing that was going on was we were about to sign our LRSA agreement with ARIN. And once we'd done that, we could actually go look at signing ROAs. And there was an interesting discussion that was in an Internet 2 meeting on Radware, where an Internet 2 engineer stood up during the Radware meeting and basically said, okay, you know, the best practice for this is only ever sign what you announce. And that also kind of stuck in the back of our mind, because to do the Radware solution, we would have had to change that. So that's where Corero comes in. It basically utilizes our existing MX hardware. It has detection built in. This is one of the poorest things we had. We could not detect an attack. And by the time we had detected the attack and figured out how to block it, it was over. It also had automated intervention. So it was no longer this thing where we've identified it and we have to advertise to say out to the internet, we want to scrub some traffic. And it allowed us to do route origin authorization in the way we wanted to. I'd never heard of these guys. I had heard of these guys. So there's this integration that takes place between Juniper and Corero. And I'm not a Juniper Corero salesman. I'm probably going to get some of the technical information here slightly incorrect. But I know they have two products. One is the Threat Defense Director, and that's what we have. That's the product that works with the Juniper routers we have. They also have something called TDS, which is a separate appliance. If you're not a Juniper customer, I know you can go ahead and talk to them about that. So what is Corero Smartwall Threat Defense Director? That's a mouthful, so I'm just going to call it TDD. It's a software-based solution that works with Juniper routers, which can mitigate volumetric DDoS in hardware. And it does this because of the Trio-based chipset that exists within the Juniper MXs. And like I mentioned, there's an appliance as well. So we're going to watch a short animation here of how Threat Defense Director works. And what we're going to see is traffic from the attacker going through the MX to the victim. And all the square boxes below are the TDD solution. So here we've got normal traffic. It's being sampled off to this box called the NTD. Attack traffic happens. Sent to the CMS. The SWA sends a little green instruction up. That's a block. The filter's now in place. And what we're seeing here is telemetry being sent back during the attack to the SWA, which is the Secure Watch Analytics device. Okay, let's look a little bit more in detail about how this works. So let's see, does this work? Okay, so they have this box called the NTD. This stands for the Network Threat Defense Director. And Network Threat Defense. Think of this as basically a snort box on steroids. It's got a bunch of signatures in it that are configured by this thing called the CMS, the Central Management Server. So you configure your policies here, it sends them to the NTD. You receive sample packets that you set up on your Juniper MX. And we do it at a rate of 1 to 1,000, which is plenty for an attack. Once something comes into the NTD that matches the signature, it sends an event to the CMS. Now, the CMS has some extra checking going on here, where essentially you can say, for these certain networks, I'm not going to take an action. If it sees an event, it sends it to the SWA. The SWA, which stands for Secure Watch Analytics, sends a netconf instruction to the Juniper router. This all happens within seconds, and you're blocking the traffic. And you're only blocking the specific attack traffic as well. And the whole time this is going on, the Juniper MX is sending telemetry back to the SWA. So this works with our hardware because the Juniper routers have this thing called the ephemeral database, and it applies a very specific flexible filter that only blocks the attack traffic towards the victim. So you don't want to block the source IPs because, as everyone will tell you who knows about DDoS, those are usually spoofed. It also does IPv4 and IPv6 because we're an R&E university. We have a lot of IPv6 traffic. It has the ability to do a version of FlowSpec, and it has the ability to do limited remote trigger black hole routing. So if you detect an attack, you can send an RTBH route up there as well. And you can send that RTBH route to Juniper or non-Juniper routers. So we have a license to block a certain amount of traffic. And we've been essentially blocking traffic in an automated fashion since May 23rd of 2023. But prior to May of 2023, we essentially operated this for a year in what's called monitor mode. Okay, this is a very busy diagram, but what I want to point out here is the TDD is over here and it's behind a firewall. So it talks to nothing else. It's restricted both inbound and outbound. The SWA component has this brown line that goes off to a management network. It talks to our Juniper routers, and when it wants to send a specific netconf instruction, it does it over this secure network to what's called a routing instance called management Junos on a Juniper router. Now we have a purplish line that comes back here. I think it's purple on this slide. Can't tell. And that's telemetry coming back to the router in real time. Now, because we have this secure routing instance on the Juniper called management Junos, it doesn't have the live traffic within that. We have to send the telemetry information from a loopback address. So it's very flexible in how you can deploy it. The other thing I'll point out is we have a remote campus over here that's many miles away. The Corero allows you to send the sampled packets back either via a GRE tunnel if you've got very remote sites. But in our case, we have an Ixia fabric. So we're able to essentially send the traffic out of the Juniper router as if it's physically connected to this device. So it's very flexible in allowing you options in how you wish to deploy it. Okay, so we spoke about this ephemeral database as one of the reasons why Corero integrates with Juniper. So I'm going to read out the description from Juniper's definition of the ephemeral database. It's an alternate configuration database that provides a fast programmatic interface for performing configuration updates on devices running Junos. So this is how the Corero is able to send instructions back very quickly to the Juniper router. And the ephemeral database is not part of the actual configuration. So if the router were to lose power, the ephemeral database goes away. And when it comes back up, you just have the config. So you don't have to write the config or save anything. And this is actually the example of the template that gets applied to every Juniper router, where Corero is going to insert a term wherever it needs to. So let's look at the second thing that makes this kind of neat, which is the flexible match filter. So Corero has the ability to write a custom destination filter. You see a destination address here. This is on our network. It's not blocking the source. And it only blocks the specific attack traffic to the victim. So this is kind of what the scrubbers do around the world, but we're doing it live on our network. So here you can see we're looking for a packet with a particular packet length. We're looking for a packet with a particular TTL, and we're looking for very specific TCP flags. So the second example here, and I want to focus on this section here, which is this flexible match mask. Okay, so we're starting at layer 4 here, and we're looking at byte offset 33. Now, what this actually means is we're looking at the 34th byte, because they like to count from 0. We're going to match all the packets here. We're going to do it for 32 bits, and we're looking for a specific prefix. These are very granular. They only take out the attack traffic, so it's very safe. This is better than the days of remote trigger black hole routing, where essentially you would block an entire IP, and it would do the attacker's job for you. And we spoke about telemetry. So whenever Corero triggers and it actually sends up a flexible filter into the router, it also, as part of the template there was a place where it counts. So what you're getting during an attack is you're getting live counters going up. And this is what tells the SWA as telemetry coming back that the attack is still ongoing. When it's over, it removes the attack. Okay, we're going to watch a second movie here, which is a demo. This is an NTP reflection attack that's going to be done as a carpet bombing network to an entire subnet, a spread spectrum. We're going to see it identify the attack within seconds, block it using a subnet rule, and then it's going to move to specific IP blocks as well. Okay, so on the left here, this is the central management server, and it's already seen the attack. This is where you configure the policies as well. So what we're seeing now is the SecureWatch analytics box. It's telling you how much traffic is live through it right there, but it's already detected the attack. And what we're seeing here is this is a subnet block. So it's filtering right now based upon an attack to the subnet. And I'll speak more about subnet rules a little bit later. Now, this is neat because I've captured a lot of data, but it's very hard to capture an attack going on. This is Splunk behind the scenes here. And so when I do a search for an attack after the fact, it never shows the current data there. So now we're attacking, we've got data coming live via telemetry from it. It's talking about what the attacks are and the IPs under attack here. It's stopped. And within a few seconds, it's going to remove the attack, the flexible filter. Okay, and because this is Splunk behind the scenes, there's a lot of rich data here. This Juniper demo is logging into the SWA, and they're going to look at attack traffic with very rich reporting. Now, even though these are canned reports, because Splunk is there, you can actually dig in and look at a lot of data on your own after the fact. And I've got a few examples of that later as well. So here we can see very rich information about source desk port, destination IPs, source IPs. I believe there should be some geolocation information here as well. There we go. Source country, source ASN. Remember that a lot of this stuff is spoofed during a DDoS attack as well, so you have to take it for whatever it's worth. Just waiting for the movie to end. Okay. Okay, this is the front page of the SecureWatch analytics box. And essentially, the way the SWA looks at Corero is it's got one detection engine and 5 telemetry sources. This is one NTD box that's receiving the sample packets and 5 routers that basically send it telemetry. Now, this is a slide that I have a little bit later as well. This is an actual attack that took place on the Stanford network, and I'm proud of it because it's very hard. You know, when you search in Splunk, these are always at the current rate of whenever you're doing the search, not during the attack data. So the SWA is also what monitors the entire application here. It's monitoring itself, it monitors the CMS, it's monitoring the NTD. Down here, it's looking at the telemetry devices, which are our routers, and we have 5 routers on the border. Over here is the device IP. This is what the SWA talks to on the router, and it's different from the telemetry IP. So once again, it's very flexible about how you can deploy it. Okay, this is the central management server, which is where you will configure policy. So it's got a slightly different view of the Corero product. It talks to Stanford having 1 segment and 2 interfaces on the NTD. Okay. This is where you will configure things. So there's rules, packet thresholds, and bit thresholds. And what we generally do when we're tuning is we're going to modify these things here. But what I wanted to point out was you've actually got a rule here. I can't read it from here, but I think it's 2091. But there's a bracketed one underneath it that's similar. That's a subnet rule. So think of it this way. If somebody's attacking you at a rate of 50,000 packets per second to a single IP on your network, it's great, it kicks off. But what if somebody is attacking 10 hosts on that network, slightly less than that? That's what the subnet rule comes in. That's pretty valuable as well. So here we see the flex rules. They're the first rules to trigger in most cases. And These are for things like NTP reflection attacks, but they're also what we use to egress certain traffic. So within our tool belt of making this work at Stanford, we've set up egress rules for certain types of test traffic. So think of this as maybe an iPerf test box or a perf sonar box, that kind of thing. We also use this specifically for the Fionas that exist on our campus. And this doesn't work like a traditional firewall either, because rules trigger based upon thresholds as well as packet matches. So the smart rules here, they all contain whoops, I went forward too much. They all contain the word floods too. And there's very subtle wording. This one says same source port, this one says same port, and this one just says to a destination IP. But there's lots of signatures in here that are part of the bread and butter of what Corero does in detection that block all different types of attacks. And then the last thing here is this smart rule scaling. This is something that we use in our tool belt to basically help us tune the network for certain heavy hitters, I would say, things like our research nodes that essentially the baseline we have for the campus, they exceed that. We want to provide them with protection. We can throw them into a smart rule scaling rule. So what is normal traffic? Well, our normal traffic is definitely not what Corero thinks it is. This is a graph basically representing the number of hits we had per day over a period of time. And what you can see here is early on, we had a lot of hits. So traffic on a research network is different from most enterprise networks. And it ensured basically, as soon as we turn this on out the box, we would have many false positives. But what I want to say is we were operating this in what's called monitor mode. And this is critical because we were essentially looking at how we would baseline what our normal traffic looked like. So of course, we have higher bandwidth nodes than an enterprise network. We have a creative student population. We have iPerf, perf sonar, strange research traffic, large file transfers, and elephant flows. So this represents the first time we went to any training. So like I said, this was a very fast-paced project. We were able to go to training here. And myself and my coworker, Andrew, represents us doing our own training here, our own tuning. We put it into the network in June, right before commencement hit. We have a commencement freeze at the university where we can't make any changes. So with the help of Juniper, we were able to basically get this crammed in within a month. But the students had left. So what we see here is this is, what happens at a university at the end of summer? Well, the students return, right? So this represents us having tuned in here, thinking we were doing good, but the students returned. We had to figure out and understand what was going on in our network more. So we still saw way too many false positives over this period. So what we decided to do next was we said, we need a little bit of assistance, professional assistance to help tune this. So we engaged with Juniper Professional Services, and we started tuning with them in February of 2023. We actually noticed an immediate change here. It's very hard to see in this graph, but there's a real flattening here. And this is student population around, everybody's back on campus. There's a little anomaly of double events there. We were essentially setting up, sending data to both our security group and to our NOC. And so we started counting events multiple times. So when we would work with Juniper Professional Services, we'd sit there and watch what attacks would trigger. And we would come up with essentially, okay, this attack happened at this date. We're going to increase some values and set it to a new value. Some of these things were legitimate. Some of them were real attacks that happened on a small scale. Most of them were false positives, and that's what we had to tune out before we wanted to turn it on. So we studied the rich data, both in the Splunk interface, and we also finally turned on a bunch of rules that we didn't know we were supposed to turn on. They hadn't gone over that in training, and the professional services helped us turn on a bunch of rules that help protect our network. So this is a zoom in on when we did professional services, and this is that little anomaly at the end there. Okay, I'm going to shift the time range out once again. I know it's very hard to read those dates. It's impossible for me, and I'm much closer than you. This represents winter break for us last year. And what happened was when we see somebody hitting the rules and the false positives, we'll take actions. We've got these flex filters we can do. We can shift them into a high scale group because we want to protect everybody on our network, right? We didn't take any action of this guy over break, and they didn't complain at all. Okay, this one is an actual real attack that I'm going to go over in detail towards the end. So we talked about this smart rules scaling thing that we have here. And what this allows us to do is we have research nodes, we have sort of an administrative network or a business network, one might think of it as. We want to tune this for the entire network. So what we did was we created policies based upon what the normal network looks like. And these scaling factors allow us to basically say, we want to treat research, maybe we'll give them 25%, 50% more. So it gives us a very flexible way to essentially protect everybody on our network. Okay, how do we get alerting? Well, everyone knows this interface. This goes off 7x24 on my phone. What we see here is that these things come in within seconds. When the SWA sends out a filter, it also sends out an alert. We get them immediately. And this is actually an example of a host that we saw alerting, and we moved them to a higher scaling factor. Okay, so let's talk about some of the data that we've actually seen. Now, you saw on that graph I presented earlier, there was a lot of blue lines on the left. We're going to ignore most of that data because it's a lot of data, and we're going to focus on essentially looking at the data since we engaged with Juniper to do the tuning. So what we saw was we saw about 47 subnets that have been attacked since we turned the TDD on in the tuning phase. And most of these were false positives. We saw 85 separate IP targets that got attacked. And a lot of these were also false positives. Some were real. But one of these things is because we have a central NAT solution, and that's one of the struggles we had with this product. So here we see an example of false positives. This is our genetics high-performance computing network. Oh, and look at this. It's an IPv6 target. TDD works with IPv6. Yay, IPv6 is being treated. I see a smile from Eric there. However, it was another false positive. But this was actually on the same high-performance computing network as well. But we're able to basically look at this, and we move them into the high-scaling group. There's very few needs to actually set up a flex rule to sort of exempt the traffic. Okay, so central NAT. That's one of the biggest things that has triggered Corero over the past year or 2 years. And the reason for this is because the way we have our central NAT set up is we policy route people that need netting to some central places. And what we do is we stick behind a single IP address about 126 hosts. And each of those hosts gets a port block of 512 ports. So when those 512 ports are talking out to the internet to a single port, this looks like a signature on the Corero. So what we do with that is we look, and if somebody is triggering and they're repeating often, we will try to go reach out to the client, and we'll probably move them to maybe a public IP. Or we actually have a one-to-one NAT solution. We actually had a server that was trying to send some sort of data out to Google, and it was doing this at 10 gigabits per second through our central NAT solution. Okay, let's look at some of the attacks now. So this is a real attack that happened against web.stanford.edu. And we had just put Corero into production mitigate mode May 23rd. And during our commencement, we're not allowed to make any changes to the network. So that's why it was great. We jammed this into mitigate mode right before commencement. And sure enough, June 8th, we got 2 million packets per second and 21 gigs towards our web infrastructure. So the timing was really good on us turning it on to mitigate. Now, it's targeting our web.stanford.edu, which is not the same as our www. These things kind of overlap and complement each other, but we do have a presence on campus as well as the cloud. So here's an anatomy of the attack. Now, that little red squiggly, that's the attack. And this is not the attack traffic. There's no data here about the attack right here, because this is current. The attack started around 9 p.m. and it was over within 20 minutes. When the olden days, when we would have to go look, figure out what was being attacked, take an action, this would have been over. We took no manual steps. It was automatically detected. It was automatically stopped. In the top graph here, we're seeing different signatures being matched during the attack. And at the bottom here, we're actually looking at the different types of traffic that they were using to attack us. So this is the Secure Watch analytics, and there's lots of rich data here. This is data from the attack, and I'm going to zoom in a little bit. Okay, so there's a wealth of information here, and because it's Splunk behind the scenes, we can actually drill into each aspect even more. So what we see here is we've got protocols, we've got fragments, we've got packet length, source IP, but as much as that can be trusted, right? Because this is DDoS, you usually can't trust that. We've got a source port, destination IP, and a destination port. Now, if you look at this right here, there's only 2 pages of source IPs, and it's about 5 IPs per. So we got DDoS by 10 IPs. We go look in Splunk a little bit further. It's actually 664 IPs were attacking us at that time. You know, we got this politician out here these days who's fond of saying Russia, Russia, Russia. This was Russia, Russia, Canada. So regardless of who it was and the source IPs, this is not normal traffic, and it was a legitimate DDoS attack. And this is the flexible filter that got applied during that time. Very specific, things were used here to basically just take away the attack traffic. And so during this attack event, nobody knew that our web infrastructure was under attack, and everybody was still using it. As a matter of fact, if we didn't point it out to people, nobody would have known. So let's talk about the second attack. Cameron, do you know how much time I have? Does anyone know how much time I have? Almost 5 minutes. Perfect. Thank you. So we thought the attack against web.stanford.edu was large. So this actually happened a month ago. So just in time for CNIC. Thank you, whoever did that. I appreciate it. All of the traffic was dropped by our border routers, and there were multiple concurrent DDoS attacks that took place, matching many different signatures. And what we found out was that there was various parts of our network infrastructure that were actually targeted as well. The packet rate for this reached 30 million packets per second, and the bit rate threshold was over 80 gigs. I'm being conservative with these numbers here. So what we see here is an overview of the attack on the dashboard. And like I said, I'm searching after the fact, and this is only showing the current bandwidth while I did the search. So this packet graph, though, down below, this is actually the attack here. And what we're seeing here is this is over, it's very hard to read, I apologize, but this is 40 million packets per second. Now it's combined with our good traffic, but it's 40 million packets per second. And you can actually see here, this is relatively our normal amount of packets per second throughout the day. We hover around 3 million. So this is the megabits per second view. And what you can see here is we're around 120 gigabits per second there. That's quite a lot of traffic. This isn't normal unless we're doing supercomputing or something like that. Now, I'm sort of proud of this graph because I was sitting at my desk during this attack and my phone was buzzing like crazy. And anyway, I logged in and I actually got a slide of the attack going on. So what we can see here is the good traffic was 30 gigs at that time. We had 3.5 million packets per second. This is the very start of the attack, by the way. It changed over the attack cycle. And what we saw here was there was 22 megabits being blocked and another 2.2 million packets per second being blocked. We also have some rich data here about what the attacks were. So there was 2 signatures early on that I'm going to talk about a little bit later. They were 2067 and 2069. And what else is good here? Oh yeah, and this is the data about what was actively being blocked. This, I believe, is the start of the fragment portion of the attack. Okay, this is 43 million sampled events at this peak. So towards the very end of the attack, somebody was trying to, it's kind of like a fireworks thing at Disneyland, right? Right at the very end is the crescendo. So anyway, there's a lot of rich data here. So this is showing the number of events, and this is showing the different signatures that were matched over this time period. Okay, we've got lots of very rich data here. So I'm just going to thumb through these. This is kind of like what we saw in the demonstration. These are great reports. I actually automate these reports going to my manager weekly. Lots of great data, and this is per IP if you want to. Third example of that. And remember, because Splunk is behind the scenes, we can actually dig in and look at these. So this is attack 2067. And this is a DNS query response. So they were trying to overwhelm our DNS servers with specific types of attack information. And what we see here is it's all the same destination port with a source port of 53. This is all UDP, by the way. You can see that from, I think, there. And we've got the source IPs here. This is 206. Did I advance? This is 2069, and this is UDP fragments. So you'll see here, it's the same kind of destination source port, but these were fragmented packets being sent. It matched on a different signature. And this is 2023. So we'll see here that was this UDP 179. Now, if you go look in Etsy services, Google what this port's for, it says BGP. Nobody uses UDP 179 for BGP, so this is not legit. And you can see here the signature of this is it's all different source ports at this time. So like I said, there's very rich reporting here. This represents top 10 victims by total gigabytes blocked. Then we've got this thing that's talking about the top 10 attack vectors. So it's the types of traffic here. This is, I think, fragments. And we can see here the total amount blocked, and it breaks it down by IP address right there. So like I said, super rich data, and you've got Splunk behind the scenes where you can go dig even further on your own. Okay, so in summary, 19 targets, 30 million packets per second, 80 gigabits per second. It was good. So what were they looking to target? So a lot of these attacks, they actually don't even know what they're attacking. They'll send it to IPs that don't even exist on certain subnets. They're guessing as well. So several IPs were not real, but 4 of the targets were actual router IP addresses. So they were actually targeting the network infrastructure. We have this network self-registration network, which is where you plug in your laptop and maybe you had a virus on it. It might have sent a bad packet out. It upset somebody. 3 targets were random test networks. I have no idea about that. But this is what was very alarming to me, and why I brought this up to our senior management, was they were targeting our DNS and Active Directory infrastructure. The last one here, this is, oh, time's up, sorry, done. No. The remaining targets were research networks. So we're a research university. We have a faculty member who likes to scan the internet at least twice a day, and he makes us lots of friends. We have a very close relationship with the computer science department, and we do support his research. Now, remember, we don't exempt his traffic. We've just put him into a high scaling solution, and we're protecting him as well. Okay, so summarize, why do we like this? Okay, we had no detection solution before, right? We're able to automatically detect and immediately block attacks now. The flex filters allow this to do this cleanly, so we're only targeting the victim's IP and removing the malicious traffic. We haven't had a single complaint about blocking anyone so far. And the ephemeral database is basically what allows Corero to integrate with our Juniper routers, so we don't have to put an extra device into the network. Remember, I said Corero's another company that I don't know very much about. They have an appliance, but I would never advise us to go put another bump in the wire. And as I mentioned, we do not try to exempt anyone, so we're protecting our entire network at the moment. I'd like to thank specifically Andrew Roderos from my team. He set up all the VMs. He helped with the tuning. He kept everybody honest on the project. He asked incredibly insightful questions. I want to throw out a specific thank you to this gentleman, Laurent Pamel of Juniper. We had a month to set this up back in 2022. We mocked it up in a lab. We ran into some challenges with some old hardware. Laurent was he helped us basically figure out what was wrong and get it put up into the network within a month. I should also thank the rest of the Juniper sales team because they helped us be successful. So thank you, Jay Roses, Sandeep Shadapuri, Mark Cates. And finally, Stanford University networking team. We get things done. And thank you all for listening. Are there any questions? If you don't have questions now, you can also come find me at lunch or at one of the receptions, and I'll be happy to talk. Go for it.
Hey, so it sounded like you guys were using telemetry sent from the routers back to the Corero solution.
You speak into a little bit.
Yeah, so, that's better. Yeah, it sounded like you were using telemetry sent back from the routers to the Corero solution. I was curious what type of technology that is. Is that GNMI or otherwise?
Wow, this is kind of why I wanted somebody from Corero here. I'm trying to think. So it's using what is the telemetry information you might find out. What is it? It's gRPC. I'm using the wrong term here.
That's right.
There's lots of things like that. It's using standard telemetry mechanisms. So we're in the process right now of a tool called Paragon as well. And the data it's sending back from the routers is something like that. I'm sorry, I don't know the answer to that.
No problem. Anyone else have questions?
Thank you all very much.